thank you, Chris, for your kind introduction. I need to make one correction. I'm no longer the scientific director of the Foreign Council. It may be my fault because I may have forgotten to identify. So I'm just a professor of science education, science and mathematics education, mainly science education, by the way. And thank you, of course, also for the invitation to speak here. I'm new to this network, and it's funny to see how many networks there are regarding education and learning, and I think it's a good thing that we try to make as many cross connections as possible. So I'm happy to be here. And as a newbie, I also like to introduce myself a bit more. Like I said, I'm a professor in science education. I have a background in theoretical physics. It's a long time ago, but I still see myself also as a physicist. But I still follow that. I did a PhD in Eindhoven University in 1993 in structural technology, and that was really the start of a career in technology enhanced learning, especially computer simulations for learning, computer-based modeling for learning. And my passion is always to try to use those devices, those instruments, to teach about understanding what science is really about, and to teach about scientific literacy. Because I think my main conviction is that it's very important that we train, educate a very scientific literate public citizens, not only the ones who will be working in science, but also all the other people who need to have a basic understanding of science to be able to function as a citizen. And I think the recent past, the pandemic has given us quite some examples why that is important. So what we want to reach in science education, and that's my passion, but I think that is shared by many science educators, is first of all to have some basic knowledge of science, but also to see something about science in society, and to see how science functions in society as something that as a driving force. Not as optimistic as that picture. I don't believe that science will solve everything as such. It's mainly the interaction of science, humanities, the way people think, convictions that's important here. And in order to do that, we need to do actually 4 things. And I borrowed this from Dennis Hodson in a seminal article from 2010. Of course, you have to learn about what the science is about. So if you learn physics, you have to learn something about mechanics, about electronics, biology. You need to learn about evolution. And well, for all the natural science, we have some basic topics that I think should be common knowledge for everyone. But it's also important to learn about science, to learn how science works, how scientific knowledge is created, how scientific knowledge comes about, how scientists work and interact. And one way of doing that is by actually doing some science, trying to engage students in scientific activities themselves. Often called inquiry-based learning, but there are many misunderstandings about that term, so I'm not going to use it anymore. And finally, you have to learn about the role of science in society. How does scientific knowledge interact with everyday knowledge? How does it influence your daily decisions on in life? For instance, the choice whether to take a vaccination or not, or whether how to behave in an environment in a responsible way. All those questions have a societal component and a scientific component, and how they interact is an important role of science education to have students think about it. And I'm going to make a rather blunt statement about what science is. Oops. Science is mainly what we call a modeling endeavor. So everything scientists do is aimed at creating models of the world. And a model is a representation of the domain that we're studying in a way that we can ask it about how would the system behave, how can we understand, can we explain it? And let me give an example. We are on planet Earth. Earth is rotating around its axis, and Earth is revolving around the sun. And we have models about it. We can have physical models of really blocks of balls that move around. If you spend some longer time in the Netherlands, go to Friesland, where we have this great clockwork model of the solar system that was built in the 1700s in IJsselmeer. It's really not so if you ever spend some more time in the Netherlands. But we also have computational models. So even the computer code that actually can compute very precisely the position of Earth around in the solar system, and not only Earth, also all the other heavenly bodies. And we can use that, for instance, to predict when we have a solar eclipse. We can use it to compute a trajectory of a rocket that goes to the moon, etc., etc. That's why we need models. And my statement, it's blunt, but I think it's true. Science is all about creating those models. And if you really look at it, scientists really have created a zoo of models, many different types of models. Apologies for the bad quality of some of the pictures. I enlarged them a bit too much. But for instance, the model that's on the top left is a model of photosynthesis. It's a visual representation of how certain processes in photosynthesis work. So the process that plants use to convert carbon dioxide into glucose and releasing oxygen. In chemistry, we use models like this, molecular models that show the spatial structure of molecules, and using those models you can actually predict how they will interact. Again, biology. In biology textbooks, you find lots of models like this, where you have a kind of a mixed representation of a dynamic process and a visual representation of what's going on. This is about sperm cell generation, and with the arrows represent hormonal and neural connections between the various components. And this, and we make models of, for instance, of the climate. And this is what we call a system dynamic model, where we have a number of variables, arrows that represent relations. Behind the arrows are equations that can actually have a computational effect. And this one could be used to predict how the climate would respond based on the concentration of carbon dioxide. And finally, and this one looks the most boring, this is actually the one I'm going to talk about the most, is an equation-based model. It is actually the kind of model that I discovered that could be very easily made into a tool for students already in the 1980s, even before I started in PhD. Simple equations like this are really the basis of many models, including, for instance, the planetary models that I was talking about. This simply represents Newton's laws and for a mass hanging on a spring, for instance. I'm not going through the details. I know that not all of you are really into the details of science, but it's a kind of thing that scientists make to understand the thing they study. And why do we model? Why do scientists do this? First of all, to understand. If you can more or less reproduce the system that you have, that you're studying in a model, you gain understanding of it. And you can use that understanding to explain to others how it works. So you can, with Newton's laws of gravity, you can explain why the Earth is actually moving around the sun and the moon around the Earth. You can use it to predict. You can use it to predict the next solar eclipse and where it will happen. You can frame hypotheses. You can say, okay, if my model is correct, I expect that to happen. And if that really happens, you have more or less confirmed your model, but you can also reject that indicate the need to refine your model or to update your model, or maybe you decide that your model is wrong altogether. That's also a possibility. You can use it to design. Let's stick to the example of space travel. You can make models that actually simulate how a rocket will go to the moon and use that model to fine-tune your design. It saves a lot of money if you do it instead of building a lot of rockets and doing trial and error. And you can use the control system, so you can get the same rocket, but it's you can see it in other things. So you can use the model to actually check whether your system behaves like a model and if not, have small corrections on the way. So there are lots of reasons why we do model and why we use models, and especially computational models. And if you then go back to what do we want to have students to learn about models, is basically the same as what I said at the beginning about science as a whole. And as I more or less equated science with modeling, I think that's quite logical. So you have to learn what are the most common models, Newton's laws, Ohm's laws, etc. The common models that they were about. Learn about how those models came around, how scientists have designed those models, created the models, tested them, sometimes rejected models and replaced them with others. That is an important part of scientification. And I think it's important that students learn to model themselves. And I think technology offers the possibility to actually do that. And at the same time also help develop what we can call computational thinking. The fourth one, models in society, is not here, but I think I should have added it. So if you look at those computational models, those simple equations that you can put in a computer and calculate the outcomes, it is a basis for computational thinking. And when thinking about computational thinking, there are many ideas of what computational thinking is. Some people equate it with learning to program, learning to use a computer to solve some problems. I think a very important factor of that, and I stole that idea from Mike Wissenbaum, is that a very important part of computational thinking is actually recognizing the problems that you can approach computation. That at some point you may have a problem that you don't know how to solve with other tools, and that you can systematically decompose the problem into parts that are computationally feasible. So you have to find the tools, for instance, a modeling tool for taking those equations and know how to use those tools. But first of all, you have to have reached some level of abstraction to understand the problem as a computational problem. I'm not sure if I make myself clear enough, but I think apart from all the technicalities that you have to learn, this abstraction about computational modeling, I think, is very important. And if you look at projects that, for instance, Mike Wissenbaum did, it always starts with it. It always starts with the conceptualization of what kind of model do I need, computational model do I need to actually solve this problem. And in a sense, that helps you also from moving to doing math to doing physics. And I have an example of this. This is another physical system. It's about radioactive decay. I think I should explain a bit about it. If you have a radioactive substance like uranium or cobalt, the atomic nuclei decay, and the rate of decay is proportional to the amount of substance that you have. And that can be put in a very simple equation. The dNdt is the rate of decay, and the n is the amount of substance you have, and the k is a constant factor. And if you do mathematics, you can easily see that's exponential decay and write it in a formula. And You can also then nicely plot a graph doing this. You start with a certain amount of system and you see it slowly decay. And of course, decay is a constant representing the substance. For instance, for uranium, it takes 4.5 billion years before half of it has decayed. And for other substances, it can be a matter of seconds or even milliseconds. This is something you can solve mathematically. You don't need computational tools for this. I use, of course, Excel to do it, but it's not necessary. You can do the math. But suppose you have the decay product itself is again radioactive, so it also starts to decay. What happens then? We have a second substance N. N is created by the decay of N, and of course decays itself, so we have 2 Ks. And if you then try to solve it mathematically, just with paper and pencil, you're stuck. You can use some techniques to approximate it, but those are not the kind of techniques that an average secondary school student would be able to do, even if he or she is advanced in physics. But if you do physics, you can do and do computational modeling. You can just put these equations in the computer and use the computer to approximate it, and you add a second line for M. It first increases because M is coming in due to the decay of N, and then at some point it starts decreasing again and you reach a certain max. And the computational tools allow students to, first of all, formulate those equations without having to worry how to solve them mathematically. And you can play around with factors. You can even add a third substance if you like. So it becomes what John Ockburn at some point called a kind of clay that you can play around with to actually express your ideas and immediately see the consequences of it. And I think that's a great power of computational modeling. And then, if you are learning to model, what do you do? What are you doing when you are modeling? And like I said, it first starts with abstraction. What am I really modeling? What is the kind of thing that I'm thinking about? So you have to define your problem. You have to define the boundaries of your problem. You have to think. First I said conceptualize, but that didn't fit in the circle, so I made just make a think. And so you have to make assumptions. For instance, what do I assume when I model planetary motion? Well, I assume there's no friction. I assume that Newton's law of gravity hold, things like that. And then you do the modeling, you enter the equations that match your assumptions. And you can do this in using one variety of tools that can be dedicated modeling tools for education, and there are quite a few around. You can also just write some Python code. There are many ways of doing it. Then you test it, you simulate, you do the computations, you conclude, you decide this is the model that I want, what can I do with the model? In many cases, you will find, okay, this model is not exactly what I want, so I have to revise it, so you go back, you have this loop within a loop, until you say, okay, I understand this part, maybe onto the next problem later now. That's kind of modeling cycle that I think is important to see that students learn to use, but also see that scientists basically use this kind of cycle in their work. And then, importantly, in that respect is also when we learn students how to model, what do we learn? I want them to learn about modeling, the so-called meta-modeling knowledge. For that, we have based ourselves in our group on a model of modeling. You can get quite abstract and meta if you're talking about this. By a group from Humboldt University, led by Annette Oekmeijer 2000. And she said, okay, there are basically 5 aspects of model that you want students to know about and be able to talk about. The nature of models, what really are models, why do we use them? Can we have multiple models for the same problem? The answer is yes, because you can have different perspectives on a system. So you can have different kinds of models that about the same system, but then highlight different perspectives. How should we test models? Should we test and how should we test models? And how should we change in the depth models? Those are the kinds of aspects that you want to learn about. And Wouter and colleagues have indicated 3 levels and 1 initial level for that. And what we do is we use this framework, but for every kind of new modeling domain we're looking at, we find you have to adapt it specifically to that domain. So I already talked a bit about computers and computer modeling. I want to make a small sidestep to introducing technology into the picture. And I may not be as optimistic as some others that I heard yesterday. We have lots of new technologies, and I tried out this part of the presentation to my local group, last week, and they called it what, and they said, okay, it looks similar like the 5 stages of grief. First is always, oh, we have the new technology. Great, look at everything that we can do. We're going to use it everywhere and all the time. I think we've seen it a lot of times. We've seen it for calculators, for robotics, for the World Wide Web. It seems like the panacea solves for everything. Then something like, okay, so that means that we don't have to learn anymore. We have Google, so why learn anything because we can Google it? Okay. Then some fear. Oh, but children don't learn anything anymore because they are only Googling and they don't really think. Or in the case of a calculator, they don't learn how to do arithmetic anymore. They just have a button on the calculator. And then something, oh, this is going to change education completely. Yeah. And my personal favorite is this one. The role of the teacher will change from source of knowledge to a coach. And if I want to say one thing, that's not true. It's absolutely nonsense that the technology will radically change the role of the teacher. Of course, teachers will do change. But first of all, they've never been only a source of knowledge. They've always been caring for students, supporting them on many more things than just the knowledge part. So the idea of frontal teaching, and that teachers only were pushing information and then hoping that something came back on the test, I don't think that it's ever been the case, even in the time before way before technology. Because I think in general teachers care about students, so they also look at all the other aspects. And the other thing is just being a coach and think that all the knowledge comes from out there. You need knowledge to be able to assess the knowledge. So I wouldn't want anyone who has no background in physics coaching my students on learning physics. So, but it's something you hear quite a lot. And also when we introduce technology, we see that we are reinventing wheels on the new car that we have. And for instance, in the late 50s, the military had what we call the permanent instructions, which were booklets where if you wanted to learn how to clean a gun, you had to start at page 1 and then answer some questions. And if you answered A, you go to page 16, where the next step would be. Very tedious. And of course, computers came, then we could automate that in a computer-based instruction. So the computer would take you to page 16. And then the World Wide Web came, and what did we see? We were putting online quizzes and everything again. So we were doing the same thing, but again on a new medium. Then we had the educational apps doing the same again, and of course they change. And for instance, this is a Dutch app, Snapper, that has some advanced algorithms adapting to the students for the next questions. And the question is, what will AI do? Will we reinvent the same thing again and then with AI? Or, well, I try to do an attempt to think, okay, what might be part of the future? But as much as any one of us, I think, we really don't know. So it's just a trial. I have been working in AI education. Actually, my first ever conference was the AI education conference in Amsterdam in 1989. And then we had this kind of model for what intelligent tutoring systems would look like or should look like. We have a model of the domain, so all the domain knowledge is represented there. We have a model of the student, what does the student know? We had a tutoring model, so say canned instructional strategies, and we had a user interface for the communication with the student. That was basically the model that was there, and this time the quality of the picture is bad deliberately because it really is a picture from those times when the computers were not that good. And it was a kind of dream that you had some adaptive oversight, every student their own cybernetic teacher, personalized learning, and well, I think that dream never really came to be in the 30 years after that first conference that I attended. We have made a number of attempts and there were successes, but it has never really taken up in general education. So in reality, I think the new technology can change how we learn, and it can also change what we learn. The role of the teacher will change indeed, but I don't think they will. They will never just a source of knowledge. They never will be just coaches, and I don't think they will be replaced by computers. They can be assisted by computers. And as example, in changing what we learn, I take the calculator as an example. My work my year at secondary school was the my first one to be allowed to use a calculator on their math and physics exams. Before that, we had the what was it called? The the log rule. And the calculator really has changed what we do. We don't have to endlessly practice the mechanics of doing computations. We don't have to do more complicated calculations by heart. So that has really changed. We have to make better estimates because we still should be able to detect whether, for instance, when we made a typo in entering in the calculator. So we should have some idea of where the answer will be in order to assess what we are doing, to have some self-correlation there. We are able to make more complex calculations, but it also means we have to think about things like how many significant digits are there. The calculator will give up to 26 digits, but are they all significant for the problem at hand? So we have to think about that. So there's also new things that we have to learn. And a question, and I don't think it's ever been solved completely, is how much understanding of the basic operation do we really need to responsibly use a calculator? And I try to extend that now for generative AI. And I'm relatively newbie to using generative AI. I think as we all are in a sense. I tried to do it and apply it to modeling. And the first time I just asked ChatGPT a modeling question, I was actually quite baffled by the quality of the answer. It came up with a very sensible model with one error in it that I had to detect, but still. And for this presentation, I made some communication with ChatGPT on creating models. So my first question was, make a model of a predator-prey system. And a predator-prey system is in biology. You have, for instance, an ecosystem where you have foxes and you have rabbits. The rabbits procreate. The foxes eat the rabbits. If there are no rabbits, the foxes will die. If there are many rabbits, the foxes will procreate. Something like that. And just by asking that question, ChatGPT came up, oh, you need to look at Volterra equation, which is a very famous set of equations in biology, just meant to model these kinds of things. And it gives a application, and what I don't show on the slide, but it also gave Python code to actually run the model in Python. And it works. But where is the learning? If a student will do this, where would be the learning? Well, you can see that ChatGPT can give these equations. You can study these equations a bit, but you skip quite a part. But you also have to know that you are really looking at predator-prey system, which is a very specific term in biology. So the terminology is okay. ChatGPT can generate differential equations, and of course, math is also a language, so like the large language model can handle that. It gives a representative model, but only a very shallow explanations of a parameter. So it can be useful, but only if you already know what you're doing in terms of learning. Then I try to make it a more conversational mode. So I said, can you make ChatGPT a modeler partner and have ChatGPT do the hard work, for instance, writing the code, while explaining what it does, and also while seeing and checking what the modeler, the students, I try to name the student, what the student would know. So instead of just asking about can you make a predator-prey system, I said, can we have a conversation about modeling population dynamics? And then the response is really different. It says, okay, you have these concepts, and if you look down, it was quite an extensive answer. You say, okay, we have these different kinds of model that you can use. We have several factors, well, the thing that human activities can play a role. There are many applications of this. And then it asks, would you like to dive into a specific model and go on? And I said, yeah, I like that. But the fun thing is, in that case, and I think this is way more useful, it has an open question. So it required the user to actually think, okay, what am I really asking? What am I really wanting, needing here? It answered the question, and in order to actually answer that question or make a choice, you need to think. You are in the cycle of modeling, you are really at the think stage of what you're doing, and maybe also the design stage. So I said, I want to discuss an ecosystem with one predator, one prey, and then investigate the effects of human intervention. Okay, on we go. It came up with the same logical Volterra equations, a bit different way of writing them down, but essentially they're the same equations. It explains them separately, and then it also explains the relations in the model, and it offers a number of human intervention scenarios, because that's what they asked. And okay, we make this model, and for each of the scenarios we give a first attempt, and then we should like to simulate one of them. And of course I said yes, and well, first of all, another time out for this conversation. It kept coming with questions. And it requires the modeler, the student, to really think at a higher level of abstraction than the student would do at the moment that he was just building equations. Because then the focus would really be on the technical part. So I'm actually quite happy with this in the sense that it forces students to think more abstract. But of course, like everything with ChatGPT, there can be errors in the models it makes. So there's also this part that you need to be aware. Okay, I may need to check the output. And the conversation went on for a while. It actually came out with various different kinds of Python code. that I could actually run. And my idea now is I haven't got to do it, is to implement this in what we call a Jupyter notebook, which is a kind of interactive text where you can have Python code behind the scenes, and you can actually link that to ChatGPT to to actually make it an interactive document, and maybe also limit or prefabricate the interaction with ChatGPT there. That's really work in progress. Well, not really in progress even in the conceptual stage. Then another part, I tried to turn it around. So I said, what's this model about? The NDT equals K times N. And you might remember that it's the radioactive decay on some earlier slides. And well, it says, well, what it is. It was able to recognize it. It was able to solve it, which is easy for this simple case. The second case I haven't tried actually, but it probably would come up with a computational answer to that. And well, it shows the various domains of application of that model. And I think that could also have use in a dialogue about models where the student is the one entering the equations, and ChatGPT will be the kind of partner to converse. So every time I'm optimistic in the sense, okay, I see really great opportunities here for ChatGPT to really use in my small scale. I'm a small scale person. I don't think about large implementations of ChatGPT. I think that's for other people to think about. I like just to really focus on these one-on-one interactions with students. And at one side, I'm optimistic. I think, okay, ChatGPT gives very sensible, usable output. On the other hand, I'm sometimes afraid that students, on how to teach students to use that in a critical way. One example, not directly related to modeling, but some students of mine were in a lesson study, and I will talk about lesson study well in a few moments. And they were designing a lesson that included a quiz, and one of the quiz questions was about the speed of sound, referring to an old experiment done by Isaac Newton. And the answer that she gave was a factor of 2 off. And I was thinking, okay, was Newton wrong, everything? It appeared that she just had let ChatGPT solve the problem, and ChatGPT dropped a factor of 2 somewhere along the way. So, and what really struck me, she had a bachelor in physics, and she didn't recognize that it was wrong. And that really worried me. So it's, well, I think she learned from this experience because we had a tough conversation on this. But it's, the kind of things that we really need to think about as well. But back to this, what did we learn about understanding modeling? And I think what ChatGPT can do, if we do it rightly, is having basically the same kind of skills and meta modeling knowledge that Gunborn started with, but maybe at a bit higher level of abstraction. So I think we can keep the framework. We might reformulate part of the self here, but I think it actually makes it more explicit that thinking about models becomes more important than just doing the model. So we have some new things and some remaining things. Remaining is you still need to really think critically about the assumptions you make. The 5 aspects from Umar Wilson, I think, are still valid. Modeling is still an inquiry tool, and you have to understand some of the underlying principles, about mathematics, about the relations, about how in principle you solve systems like this. You can't just rely on the Python code. You also have to be able to critically evaluate if the output of the code is really what you expected. prompting becomes the new skill when it's, that really becomes important because you see the way you approach it really makes a big difference. One of my worries then is, okay, we have this version of ChatGPT now, next year it will be completed well, but it will have evolved. Whatever we learn today will still be developed next year, I don't know. It is more on checking the models rather than just building the code. You think in terms of equations rather than code, and I think that's a big game. And you will become able to work with more advanced models, more complicated, because part of the hard work is taken out of you. I'm talking longer than I had planned, but that's always the case. I'm going to switch to a completely different chapter. I promised something about lesson studies, so I will tell something about it. It's not necessarily related to just modeling or science education. It's actually used in, it started off in Japan in mainly mathematics education, but now if you look worldwide, it is used in many domains, many contexts. And I'm telling you about it because I think it's such a powerful way, and you can see it really as a kind of grassroots way of inventing new ways of teaching and trying to spread it and really taking them into educational practice. What I like about it mainly is that you work with teachers, you do your research together with teachers, and take them along in the thinking process. And that's really a different way of doing research from your ivory academic tower, thinking about going to school, collect data, and then come back. So what is it? It originates from Japan. And some people in the lesson tutor community think, okay, that is the original and we should do it this way. I don't think so. It has developed and spread internationally, and we see many variants of it. It started as a method for professional development of teachers. I'm also using it as a research tool. In Japan, it's really integrated in, well, not the whole school system, but many schools use it as in a daily practice to improve on professional development. And it is I think, a very important factor in Asian school success. And I go back one slide. Yeah. Let me just show what it is. In lesson study, you work in teams of teachers, typically 4 to 6 teachers in a team. And you start from a goal, and that could be, well, let's see, I want to try out how ChatGPT will work in my modeling lesson, but it's something I would do. But my colleague Celine Groen from Windesheim is doing lessons about bullying, for instance. So you have a theme and a goal, and the point is you from the start you focus on what do we want students to learn and to do. So you design a lesson completely from everything you want the learner to achieve. So you don't start from the teacher, but you say, okay, I want the student to do this and this activity. I want to think this way, and I want to be able to show it and see it in this way. So, and from that focus, and in taking that focus, you also take into account the literature. You can consult others. You can well, there are many ways of gathering knowledge to take that focus. Then you design a lesson, and a lesson is what we call a research lesson. It is designed to study and not necessarily a perfect lesson. You perform it, you evaluate it. One of the team members performs the lesson and the others observe. And they really closely observe the students, not the teacher. Then you evaluate and redesign the lesson. And well, and then the cycle continues. It's basically also a modeling, like everything else. So it's not about designing a perfect lesson, it's about a research lesson. So sometimes you put in elements in a lesson, not because you think it's part of perfect lesson, but it allows you to more closely study what students are doing. So you may have a communication activity inside just to have them communicate to see, okay, what are they thinking? It's about learning about the effects of teacher intervention. And very important is to really detailed lesson design, focus on the learning of students, and a very proper reflection and redesign of the lesson. I was happy to make a study trip to Japan some years ago to really see it in practice in Japan. And we started at the university. This is one of the not the teachers, but one of the supervisors explaining what the lesson would be about, because the teachers had designed the lesson, and it's about a math lesson. Not going into the details for that. He explained what the lesson was about, and we were shown the lesson plan, 13 pages, very elaborately specified what the lesson would be, predictions of what students would do in each stage of the lesson, etc. So really trying to emphasize to make the learning visible. And then we went to school. And in Japan it can be like this. So we have a teacher here, it was a very young teacher in this case. And you have about 30, 40 people in the classroom observing. And not just standing there on the outside, but at some stages even looking over the shoulders of students. What are they doing? What are they writing? And the fun thing is, students don't care. You're completely air for them. And well, in Japan they're used to it, but we also done it in the Netherlands. And maybe the first 2 minutes they notice you're there, and then you're just not there. That's amazing. And then afterwards, in Japan, usually the whole school is involved. So in this case, all classes were sent home early, except for the one where the lesson would take, and all teachers would be in the room. We were there, so it was pretty crowded. And here, the teachers extensively evaluate the lesson. The person behind the computer over there is what is called the coach, the knowledgeable other. Usually a professor from the university who is commenting on the lesson. Something was here that in Japan is, in Europe, you're mainly evaluated by the number of publications we have. In Japan, being invited in this role really counts also for your academic stature. And then, so very extensively elaborate. So it's really a whole school thing. In the Netherlands and in Europe, in most other European countries, we do it a bit differently. This is in our lab. We have a nice lab with cameras we have a nice lab with cameras where we can observe the students. You might see one of the observers over here, writing down what this student is doing. There's another observer here, but way less observed. It was just a team, so that would be in the same, I think it was 5. It's a physics lesson, and well, in our lab we also have this possibility of having a camera right on top of the table. And again, we closely analyze the videos, etc. afterwards. And I want to show you an example, and I think I can do it in 5 minutes, about how we do it in research, because that's another part. It's partly for we use partly for professional development, but in my group we also try to make it a research method. Suzanne Janssen, former PhD student of mine, she graduated 2 years ago now. She did an extensive lesson study cycle with the school. She had a lesson study team of 4 on her own school. She was a teacher PhD student. We have a program in the Netherlands that teachers can apply for a PhD grant, and they then part-time work on a PhD, part-time keep teaching. And well, it's about that model about square prediction, but also about other models. And she had a team, and the idea was building understanding of models in the classrooms that she was studying. And she had one one group, that were two classes, where the lesson study was being done. And she had another school, parallel school, very much comparable, that were just doing well, business as usual. And she had two lesson study cycles during the school year. She had a pre and post test. She had small pre and post tests before and after each cycle. And the first cycle was investigating really what's modeling about. So she took a familiar topic, photosynthesis in this case, I think. And photosynthesis was familiar because it was still taught just before the cycle, so they knew about it. And she had a number of problem-based activities designed by the students to make explicit what they learn and how they talk about learning. And for instance, they had the group, they made group work on purpose so they could talk aloud so that we can actually follow their thinking. Similar, a bit later in the year, she worked specifically on visual literacy because of all the visual aspects of many biological models and how to convert models to text and text to models, and so learn more about the modeling techniques. So this was the whole experimental setup. And important in this, one example of the first lesson is the lesson was divided into key activities, key lesson activities that all address a specific part of modeling. We had a dialogue as a tool for model construction, and that gave us the possibility to tap into the student thinking and having and using group-based activities for that. An important aspect of the Dutch and also the British model for lesson study is that we select particular students to observe closely. So that could be students that are very strong, very weak, or maybe very on another dimension, depending on the topic at hand. And those students are really followed closely. And from that, you really learn a lot. It's something I would advise to everyone doing sometimes, just to sit in a classroom and watch one student and see how learning is. You learn so much from that. For this presentation, I put on a slide the results and conclusions from this, but it's not really important because it's not a topic. But we were able to really extract some ideas and details from the lesson study, and we saw that they gained over the school year more than the control group, especially they were able to use modeling terminology in a more natural way than the other groups, and it showed insight. And then the bonus from lesson study is that we don't only gain insight in the outcomes of what we designed, but we could follow the process of how they came about. And we could also identify the problematic moments in there. So looking for lesson study, it can be a really grassroots approach. You can just try out this simple thing. You engage teachers in research. Very important, very rewarding for the students who participate. And most of the teachers who want to do it again. You can, it's a tool to link theory to practice. We have all these nice theories about modeling and teaching about modeling. Lesson study puts you to the test. How does it really come about in the real classroom? And with teachers who really have to do it. And at the same time, so it's also a tool for research, but also for professional development as teachers at the same time. Teachers learn a lot of that. So trying to bring these two together. I was struggling a bit with that about talking about generative AI and about lesson study. And what I have in common is, in both cases, we are not so much interested, it's more like this. We're not so much interested in the end product. We're not so much interested anymore in does the student make a complete and correct model of something. We are way more interested in how did they take dialogue with ChatGPT? What are the links in it? And if I would do this in class, I would not just ask as a result for the end product, but I would ask for the whole dialogue and analyze that. And the same with lesson study. We're not so much interested at a time in a perfect lesson or in the end result. We're really interested in a learning process and see how we can make things better. So that's what the two have in common. And so you also should rethink our assessment methods, I think, if we're talking about it. We should really rethink, okay, what do we really assess? Are we happy with the students handing in a perfect text? Well, that's not so difficult anymore, handing in good text. ChatGPT has many students, and I see their English, and I think, okay, you didn't write it yourself. So, more and more, I think it's important to take the process into account there. And then my final slide. So we should also trust to rely on the process a bit more. And the other thing is, when I was preparing this, and yesterday it came to mind again, so I put this on my final slide. Already in 1991, Solomon Perkins and Logerson, they had this article in Computational Research where they distinguish between learning with the technology and of the technology. And if you look at calculators, if you look at Gen AI and all the other technology, it's a very important distinction to make. You can learn, you can have teaching technology, and students can reach a good result. But to what extent were they dependent on the technology? Will they be able to do it also without technology when ChatGPT is not available? So we really should be thinking about this. And this, well, in 1991, actually, it was an AI presentation of 1988, when computers started to enter classrooms. And I think it's just as said it now as it was then. So I think for everyone here, that's the most really. And that's my final remark. Thank you.
Thank you.